Happy Tuesday, everyone. Welcome to week 4 of the global edition of LambdaConf. And with us today, we have Mr. Jason Grafft. He is going to speak to us about enhanced machine learning and data visualization pipelines with isomorphisms. Jason is a several-time speaker at LambdaConf, and we are really happy to have him back with us for our 2020 edition. Jason, thank you for being here, and I'm going to let you take it away.
Excellent. Sorry, right last minute here, I introduce a bit of a production hiccup. That is definitely my style. Welcome, everyone. I hope the weather and surrounding environs where you are at the moment is, excuse me, as nice as they are here today. I am based out of the Twin Cities in Minneapolis, St. Paul, so I am soaking up the couple weeks of nice weather that we get a year, and most of them occur around this time. Excuse me. I have a little bit of allergies at this time as well, so my throat might crackle. Apologies on that. And other than that, should be good to go. So my talk is a mouthful. The title is a mouthful, and we're going to have a bunch of theory. So apologies. We're going to go end to end with this verbose thing, but I will try to keep the level of detail manageable and also step through in a clear fashion. I do not have the ability to monitor chats live here, so I apologize. It has to do with the screen share. Please post them. John and Courtney will be watching, be able to pass information to me. Excuse me. All right. And lastly, thank you for coming. My name is Jason Grafft. I work for a company called Relational AI. It is a startup based out of the Bay Area. We are distributed, so I have coworkers all over the United States, all over the world. We all work from home, and we are working to develop a database and compute environment with a logic programming language that is very mathematical and extends languages, or would be an extension of languages like Datalog and thus Prolog. It has a few more features. It's able to do things like recursion. It's based on a relational algebra. It is still very, very much in development. I have been setting up experimental servers with it on experimental branches for the past couple of weeks. But you'll see some of the language today. I did mostly pseudocode because it is evolving so fast. It's not really worth putting it on screen. It's still in alpha, but it is pretty interesting. It gives me a good breakdown structure for this talk as well. I have a fancy job title. Really, I am a data engineer at Relational. That is more directly descriptive of my role, but I work for the knowledge and data science team. So thus, I was handed the title of knowledge engineer instead of data engineer. So forgive me on that one. It was not my choice, but if you want to talk later, by all means, hit me up. So on with the show anyway. And I want to do a quick review of definitions because we will use these, but I will not use them heavily. So take the large concept here. I am going to move fast on the next couple slides. That's fine. We need to have our thinking tuned in a specific direction for the remainder of the presentation. This will do it for us. Graph isomorphism. We're going to be talking about graph structures because it's kind of easy in this context. Most of the diagrams you will see downstream are category theoretic. I use category theory, excuse me, but the graphs and this type of isomorphism, nodes to line, node edge to node, they do apply here. The thing to take away is that we have one-to-one correspondences down the stack. Excuse me. So every letter is represented a single time, and every number is represented a single time, and they relate to each other one-to-one. That's the important thing for an isomorphism because, as you see here, it's a bijection. Today, bijections are going to be a little more important in terms of practical definitions. So we'll skip forward. There is only one bijection in the set. It is down here, marked in the column true or false. And you'll notice that it has this same property where there is a single representation of each unique value on the left and a single representation of each unique value on the right, and one edge between each pair. So we have four values in X, 4 values in Y, and 4 edges, which do not overlap or share a node. As you can see, things like here, or we don't have a place to go there. Excuse me. This is important operationally, and specifically for what I do at relational in data engineering. You end up dealing with a lot of volume, and when data transform, they have to transform. That's where your memory hits come from. That's where your performance hits come from. That gets expensive, and the more diligent, excuse me, I can be about maintaining this kind of structure in my operations, the easier it is to reuse, be diligent and mindful of my transformations, and also account for where my application or application stack uses memory is likely to, where it might introduce its own problems and errors. So with that in mind, I want to make this disclaimer on why I called the talk, or titled the talk, excuse me, Enhancing, instead of, outright improvement, making it better, that kind of stuff. We are not necessarily going to up any type of sexy factor here, innovation, optimization, performance. We can use some cool theory to describe this, and we can break down the operations in compelling ways. But we are still stuck with algorithms being of a specific construction for various needs. Most of the time, if you're thinking in terms of information theory, which I find to be a decent crossover here between math and more hard physical computer science, entropy is a good crossing point. So we have a lot of set combinations to make. If we are thinking in terms of bijections, we have sets of X, sets of Y. When we combine those things, there's all sorts of mathematical rules that govern how the next sets are made. Category theory can describe them. My company and my company's databases uses relational algebra, and there's many valid ways to describe this. But what we're talking about really is entropy, and are we expanding the information set, or restricting the information set? And then against what backdrop, so to speak, or what does it mean to expand or restrict it? The next question then becomes, is that expansion or contraction worth the resources put into doing so? So if you have to generate a lot of facts, to use the database school of thought, if you have to generate 1 million facts to distill it to 100,000, that is probably an inefficient operation unless we have good evidence that that's a minimum form. So if we do have a good theoretical understanding of where expansion and contraction takes place, however, we are still limited by needing to define this logically and then in computer code, which also both have their own set of restrictions. So before we get high-minded about what some very cool and kind of theoretically interesting mathematical properties can contribute, we would be mindful to take these things, or we would probably do well to take these things into account. Excuse me. So here is my sort of pitch to you all, and I hope these are palatable. But I think this will at least free me from the accusation that I oversold you. Isomorphisms and realizing them inside of our code and our logical operations, they don't free us from performance issues or necessarily increase performance. They are a relation defined by theory, and we still have the problem, as mentioned above, that we have to translate theory to practice. Lastly, I'm going to pitch you on this third point mostly, that working to realize stricter forms of relations across the systems that we're building and across the functions that we're using has a good deal of longitudinal value. It's not going to hit the high water marks of dramatic optimization, dramatically reduced resource utilization runtime, but it does give us a lot of things that, at least in my small corner of the industry and where I came from in medicine, have a lot of value. Things like accountability of code and accountability of operation. I can tell you where variance may lie. I can show you how data are being transformed by my operations much more clearly. And that has implications for in industry for places like tax accounting, where I have to do a lot of trades and the IRS has rules. If I don't know how my operations are modeling those trades and I get audited, it's going to be very hard to account for the results. So this is a kind of a picky approach to establishing a well-oiled machine, or at least a better ordered one. And that's what I'll pitch you on going forward. So taking the next step into the actual part of the presentation, we're going to take a look at using Fisher's iris data set to do a classification task with the machine learning. We're going to go, the machine learning part of my talk comes right next. But we're going to use Fisher's data set. It is, the reason I picked it, it's simple. Operations on this data set are relatively easy to understand, input to output. It's accessible to a wide audience, or reasonably well quantified. And then it works well for learning, quote, quote, or example machine learning tasks, because it's a well understood and well quantified data set, and it's small enough to run most places. For our purposes, since we are doing classification, we're going to break it down into two matrices, or or several relations. I'll get to the relations thing in a second. Our data, which we will do most of our compute over, is in the data matrix, and then our labels, which are the things we're trying to predict, are going to be in another matrix. And you could name these a lot of things in machine learning. I will use a few terms interchangeably, but these are the forms we're working with. And to go back to the 1980s and echo a lot of the people I started college with, who were machine learning, data engineer type folks at Control Data and Industries here in the Twin Cities back in the 70s, before those terms existed. This is the way it's still done, and it's worth understanding. So I'm going to kind of go old school with my machine learning, but we still have, no matter how complicated or convoluted our system is, a neural net is still trying to take an input structure and turn it into an output structure. It's just doing it via a much more stochastic process, or quasi-stochastic process that's not precise. But we can do that. We can walk that path a lot of ways, and we're going to walk it in a more concrete, discrete type way by using KNN, which I'll get to right after this. As a useful aside, and something to kind of set your head about when I mentioned set operations and where they get expensive, where we go from these matrix forms, and when we cross the bridge into having to compute over this, having bytes on a disk, which represent these matrices and data structures, we have to do a lot of weird things to keep our indexing regular. This is a good example, and this is also, I understand this reasonably well because this is the form that my company's database and development uses. It is a relational structure called sixth normal form, and as far as I know, there are no more than six. I could be wrong, but it was designed for temporal data, where you have evolving sets which are linked horizontally, so to speak, linked in time. And the important thing here is you notice that each of these is a separate column. If you think of this as like a SQL table, you'd have 5 actual tables. One of the ways I describe sixth normal form is aggressively normalized. Split out everything. Yes, it's memory heavy. You need much more storage. One of the advantages here, if you have a way of describing your indexing scheme, relation to relation, coherently, this storage structure allows algebraic relationships over your data columns. So I no longer have to specify elements, and it enables things like point-free operations. I can take down operations which are normally a long time to take a good amount of code to describe. I can bring them into a much better scoping by restricting the number of possibilities as my operation chain continues, and it allows the compiler to make those decisions. But thinking about this form, which is much more natural for a computer, even if we are looking at, if we're in, Python REPL looking at a pandas data frame like this, your computer is thinking about it much more like this. And this is what becomes consequential when you have to start operating over large data sets. If you want to talk more about 6 normal form, kind of how this works, we can do that offline. But what I want the point I want to stick is these indices become both a help and a hindrance as we move forward. Because as we operate over these data, we need to know wherever in these matrices we are, and we need to know how to relate elements in the data matrix to elements in the labels matrix, because we're seeking to recreate part of the labels matrix as such. So, excuse me, I don't want to risk hitting mute right now. Had enough issues getting this set up, and it seems to be working, so we're going to go with it. But crudely, and I apologize, the dimensions of these plots are bad. The x-axis is monotonic. That's bad. It doesn't represent a thing. It doesn't represent the distribution well, because the x-axis is essentially an interval, or a regular interval. Sorry, I'm blanking on the term. It's a non-continuous variable, discrete. There we go. Since the x-axis is discrete, we do not see grouping of the points with much regularity. So forgive me on that. What I would like to point out here is, since we are doing a classification task via k nearest neighbors, what we would like to understand, or have some rough estimate of, is how the training set, or how our set used to test the data, excuse me, I swapped those up. So Y1, the blue dots, are our training set. Y2, the red dots, are our test set. And it is helpful to see how well described the test set is by the training set, or vice versa. And there's where I cross-linked it just a second ago. This is not a good representation, as I said, because the x-axis is monotonic, so it's a shaky presentation of that concept. But I think it points it out well enough for purposes that we have a reasonably good matching of the distributional characteristics between our sets. And I hope so, because I think I used scikit-learn, and they're supposed to do things like this. So thank you. And this is the test training set that the future calculations will be based off of. And we can be reasonably confident that using a nearest neighbor strategy on our test data set will be somewhat productive, because the two sets share distributional characteristics reasonably well. I apologize, my neighbor's lawn care service is here, and I'm going to go shut the window. All right, joys of working from home. I haven't tripped or fallen over anything yet, so I apologize. This might be the best y'all get in terms of dumb interruptions. But anyway, back to topic, and thinking about k-nearest neighbor classification. We need to do a bunch of iteration, because this algorithm is fundamentally inefficient, hence my warning a couple slides ago. And we're going to see that right now. But since we have good distributional characteristics and a relatively small data set, KNN should be appropriate and relatively accurate for these data. And we'll take a look at it. If my company decides to open up its language, it's still in heavy development. It doesn't have a official name yet. Things like that. The code that eventually is the code form and syntax that eventually is released will look something like this, but it probably will not have math symbols. It is being written, the interpreter is being written in Julia, and Julia REPL does allow these things, so they may, but you will see it'll be for all spelled out, things like that. But it is similar in form to this, and it's because it's a logic programming language. We're looking at things in terms of joins and in operations on sets and relations. And so what we want to focus on anyway here is we have that test set, which is right in the first line of the for all. And X is our variable, the variable that I use to describe the elements in the test set. So we're going to take each element of the test set, and then I'm going to skip to deep into the function, right into the middle, where it says top, the second time, farthest to the right, because logically this is the easier flow to follow. So right down here, if I don't know if you can see my highlighting, I hope so. Right here we have the train set, and because KNN it uses a distance metric to decide who is most appropriately grouped with who, for this classification task, we need to use that function on literally every pair of tuples in our test and train set, and that becomes onerous, is putting it mildly. I've had some discussions over this. I've been working on implementing KNN and KNN type algorithms in my company's language. The computational overhead is very difficult to deal with, as nice as these algorithms are sometimes to implement. And so that's what we're looking at here. And I'm ceding some thoughts for a second when we look formally at the scaling characteristics of this. So back from the aside, and we're looking at comparing every element in the test set, which is described by X, to each element in the train set, which in this case is described by Y, right down here. And you notice here that we have another for all loop in that inner side. And so what we actually need to do is we need to go from the outer variable here to the inner to do the operation. And then we will take what is generated from this operation and begin to work our way up the chain of functions to produce the result. So for each value, each tuple in the train set, would keep in mind these are tuples of arity 4. We have four elements in each row of our data set. So we're going to have a tuple of arity 4 compared to the tuple of arity 4 by our distance metric. In this case, we are using Euclidean distance. I have that in the appendix if you're interested, or if we have time. The important thing here is that we are getting back some sort of scalar value, which is a float. In my company's language, and the reason I have these square brackets versus the rounded brackets is formally, and it's a little bit loose in implementation right now, hence my habit of mixing them probably inappropriately. But anything with a square bracket will return a relation. It returns some sort of value. Anything with a regular parenthesis returns a true or false. And that has some logical consequences that's based on the math and the logical operations behind the language. It's pretty convenient when it comes to communicating things with your code, but they've abstracted over it reasonably well, so it's not too annoying yet. The language is still evolving. But that is, I just want to point out that this is going to return a value of some sort. And then for all of these values that get returned, we're going to have a set. We're going to take the top, and this is a function, which includes a sort and a take, basically. So it ranks the values that it's given. This is its second input right here. It ranks all the values in that relation, and then it takes the top k. That's where the k and KNN comes from. So the k nearest to neighbors, 10, 12, 3. Certain data sets are more informative at certain numbers. But we will get the top k values from this operation back. And then we're going to join those values, because if we remember back here, we had the data set and the label set. So we're going to join that relation of k length, k size, with the labels. We're going to accept that there's some magic going on to keep the indexing straight, so this is not blind. That got a little too complicated and visually distracting to represent. It's not necessary, so I cut some of that out to make it more readable. And so trust me, it's happening, and it's happening reliably. But we now, inside of this block, we have a set of distance values, and we have a set of their labels, which is the things we are trying to predict over. We're going to count the labels, which is that fancy looking L. And so we're going to take all the values in this column and produce a summary of how many unique values were in that list of K length, so you can think of it. And we're going to take the top value of that. This is naive KNN. I do not have a strategy implemented to tiebreak. You can, take that as you will with your imagination for now. Right now, it's not too consequential, but absolutely it would extend some things in the model and in the runtime, depending on the complexity of your data. But what I want out of this for each X value is I want the top one of its nearest neighbors. And statistically, that is a count via a distance metric. We're using Euclidean today. There's many distance metrics you could use that are appropriate for an n-dimensional space. But via this distance metric, I want the top, we took the distance metric, we took the top so many, we looked at the value that was the most represented in that set. That's the one we want. That's number one, iteration number one. We're going on to number two, number three. So what I just described in a little bit different way is in these column. And we're using a sort strategy kind of via nearest first. We're going to take the top K tuples. We're going to join them. Then we're going to count them. Then we're going to sort them again via a most frequent strategy and take the first. And this is inefficient. And this is why naive KNN has a scaling, an ON factor of dn squared. It's not efficient, and fundamentally it's not efficient. In our case, that translates to 4 dimensions with 150 elements n in our data set, and that's 4 times 22,500, and that ends up as 90,000. This came up recently. One of my coworkers, who is the principal maintainer of the machine learning library MLPack, did some of his dissertation on KNN, and this came up in the discussion. The data set we were looking at had 4 billion rows in it. They wanted us to do KNN on, and we were trying to figure out how this might happen. Still working on that problem, but pretty interesting. So we have this kind of gnarly, fundamentally inefficient operation. We're going to kind of take it apart in a different way. And kind of as a reminder, we're not dealing with much data right now, but as we scale up, it's going to be rough. So taking a more category theoretic view, operational view of our chain, and my sincere apologies to anyone with legitimate credentialing or skill in category theory. I do logic, and I steal things that mostly represent what I'm thinking of. So I'm a little bit loose, and hopefully the logic flow will be well represented here. If I've missed a few details, please do not be shy about filling me in. But do keep in mind my objective was not to be precise with my theoretic modeling. It was to be more communicative. So if I missed a couple of details, please begrudge me that at least. And anyway, so we have the same form, right? Except for we've split the data up now, test and train. We have the same arity4. These two together, X train and X test, make up the data set, the full data set X, right? And then we've as well divided our labels. And you can think of these as sets. I'm going to think about them as sets or relations. And yes, I did hand draw these. Computer digital diagrams are really sticky. They take a lot of time, and you don't really get decent results anyway. They don't scale. So I just left it with my hand drawings and took photos and spliced them. So I hope you enjoy. Please forgive me. But they're all in the Git repo if you want larger versions. And as we're thinking about with KNN, this kind of interior process where we've got to take apart and go step through this algorithm, that's what we're doing here. So the for all step between where that takes is our 2 relations worth of data, our training set and our test set, And by a join essentially zips them, or an implicit join makes a zip. So you have the two tuples are side by side. That for all step allows us to structures our input to the distance function, which compresses 8 values into a single output, into a scalar output, right? So we had an isomorphism going in, and we don't anymore. And so right here, we have at least a flag for an amount of waste in the pipe. This is necessary in this case because we do have to do some comparison here. But if we're looking at optimization, this is a good place to flag. When we skip to passing, we have the set D here because we create a set of it that we pass into the top function. And the top function does ordering. So we have this I value because it has to add an index. We may be able to reduce that because we're not using it really anywhere. And it's actually a bit of a redundant carry because we see it pop up via regeneration a couple times downstream. We could introduce a more efficient way to sort this. That would probably help us. And if we maintained this isomorphism, we would also cut out an operation that is quite expensive and known to be fundamentally long-winded, so to speak. We have this AND, which is a join in relational algebra. So I left it in as an AND, but you can think of it as a join, a Cartesian join, which produces our set J. Right? We have this long arrow coming because we need that label from our training set back here to join with our distance value. And so we don't have an isomorphism here because we still have that I value that's not being carried. But we are at least not having to. We can introduce the training label set at a time when it makes sense computationally to use, and we can do it after we have restricted the set to its smallest practical form. And both of those are good practice. I don't know if we'll get away with any better. And then we have also taken a small set to pass into the count function, which is going to which is a reduce, and it's going to have to iterate across that set one more time. So passing downstream here, we can at least we can be architecturally confident that we're passing a minimum set, and whether or not that's efficient is another story. But if we know that is a parameter we can focus on rather than trying to get a handle on how much is going in versus how much we need. And when things scale up, I can give a much better idea of what scaling behavior might be, or how I can shard or break up work across the system. Our count function, as I said, reduces, and then we get hopefully a smaller set. It should be as large or less. It should be between 1 and k, this set that goes into top, because we know that it is at most contains k unique values. And so if top has to do its maximum inefficiency is if it has to sort k. And if we can somehow reduce that k value, reduce k pragmatically, we can save some work going into this last function. Once again, this is something that we can pick. Why don't we just use first? It turns out representing arrays is real weird in relational algebra. There's good theoretic reasons for that, but operations like head and tail get a little funky when you are not working with an explicit array. And if you want, hit me about that offline. But that is why these functions in this particular implementation are a little bit verbose, right? And if we want to, our ultimate goal here is to get a visualization out and get some visualizable data out that contains our labels, that contains our labels, our predicted labels, and it's something that can be interpreted. I was targeting Vega Lite in my, I think in my description and kind of in my pipeline. Vega Lite is a declarative graphics API. It's pretty cool. You can define your plots as JSON objects, and then just push pipe data into them. and they will dynamically re-render. They will do a good job of understanding well-formed data without you having to fiddle with it too much, and it's nice and stable. Notice that down here, that P6, where we have a predicted label for our training set, is going to be null. And we'll see that represented in a second. So the end-to-end operation looks kind of like this. We just saw the top part where it says KNN. We went from data to top. And then we get this output data set that we have to create, because to get it back in this form, we need a concat operation to stack our data. But we now have the necessary inputs to keep it unique. And remember when I mentioned this idea of minimum sets and uniqueness became expensive, I want to point out that we've done an awful lot of work to get these values back out. And we're going to have to do some extra gyrations to maintain the uniqueness of the individual tuples inside of the sets. And that's where this computational complexity and overhead comes in, and where it can become useful and helpful to model it. So we're going to walk through this a little bit. So no fear that having to connect these dots yourself or to squint. I have zoomed in pictures coming. So right away, data to for all, right? We saw that in the earlier operation. We maintain a nice, this is a bijection. We have an isomorphism here. We have two sets that are being taken in by this for all, and they're being retained as two sets to be passed into our distance function. The distance function causes quite a restriction. It takes essentially two relations and reduces them to a set or a relation of scalar values, and that's quite computationally heavy, especially as the n of the sets increases. And for this to work, both tuples have to be of the same arity. So 4 for S, 4 for R, or 2 for S, 2 for R, etc. And as these get bigger, the operations get more expensive. But we know why, and we can plan for this in ways. We can plan to build this list via certain strategies that break up the workload, that kind of thing. We can pipe old data in because it's still relevant to pre-computed at another time where it makes sense. Then we need to sort it as we described, right? And here's where I mentioned this size of the set D in top is going to equal K, which is our K value, the nearest neighbors. And we're going to pass that property along to our joins. So we're going to take K of L, we're going to take a K number of labels from the L set to combine with the K number of Ds from the D set. Sorry for the mathematical verbal fluctuations there. Then we will join them like we described in join labels to, wait a minute, we did the join, there we go. Then we're going to count from the join to the count. One node behind. I got my lag series ordered too far to the left. We will take that count of the join we just did. Keep in mind that our join is going to have a minimum complexity that actually is based on the label set. In this case, it's simple because we have a single label. It's a short text string. If that object starts to scale up, this join gets a lot more complicated, becomes more expensive. But we know at least where it's happening, and we can focus our efforts there. And that's also a core tenet of the functional programming is this kind of logical encapsulation. If we take this join and we count it, right, we get this count value each, and then we need to take the top of the count value, and then keeping in mind that our maximum size here is going to be K, which is carrying forward from our operation, the top first, this operation here. We're hoping that we get an efficient reduction so that we are counting a successively smaller set and running the same track on shorter and shorter cycles to produce the value that we need. So hopefully this is what we get out. This just tells us it's a vertical relation, not a horizontal one. It's a Julia convention. But that's what we're hoping to get out. And this top function is going to produce L1. Then we're going to run back to the beginning and get back to here, top, to get L2, go back L3. And so when we have that, here. This arrow is the set, is representing the connection between this label and our test data set. So what we are doing now is we are building the data sets to ship to our visualization function. And we're going to assume that it's somewhere, but it doesn't matter if it's local or if it's distributed. It doesn't matter how many steps it takes. There's still a lot of IO transfer that has to go on. And if we are doing our diligence to preserve the ordering of our data, which will be reflected in isomorphisms and isomorphic processes, we don't have to transform it. We don't have to transform it too many times more than necessary to end to end. And this operation here really isn't a bad one in terms of efficiency. This is also something we can think about. We don't have to think about it statically. We could do this as a stream, something like a hot stream, quote, quote, where this is happening as data become available. This model still works for a streaming approach. If we need to hold on to, or we need to stage some data, so we pile up 12 and then we ship it on, we can also factor that in to this description naturally. And it gives us an idea of where the operations are coming from and going to, and where our data are coming from. My favorite part, and this is because, and I'm surprised it's taken me this long to say this, I come from a statistics background, specifically a Bayesian statistics background in time series, and that's has a strong crossover with my time and experience in computer science. You hold the data invariant in Bayesian models, and this gives us a good way of looking at data as an invariant quantity, and then what's happening, what we are doing to it to make some sense of it, so to speak. So with that tangential soapbox tended to, when we can think about some of those things going into building this data set to ship to Vega Lite, now's a good time to be having this churning in your head, because we actually have to visualize this stuff next. And the visualization is a graphical representation. The closer it comes to our data structures, the easier it's going to be for us to talk about, for us to represent, and for us to interpret the representation of. As a statistician, that's very important, because those graphical representations are a primary communication tool for a lot of the work that I've done. And if the relations have to be warped a lot along the chain, it becomes harder to communicate what I mean, and certainly what people may interpret goes way up. That's set problem. I don't do my diligence to keep to manage interpretations and assumptions downstream by being unclear about how I'm transforming my data. And so there you go. And that's what we're seeing in reflected. That idea, or that ideal and concept, is reflected in this process, where we've shipped a bunch of data down the line to be processed. We're pretty much forgetting about that. That has turned into a label, right? We took 8 float values and we turned it into a single text value. So these arrows, out of sight, out of mind. The diagonal arrows going down toward the bottom of the screen are the ones that are important now, because we need to build the set. And so we're going to take our test data and our test label set, and we're going to take the predicted label that we made, and we're going to join them into a set of relations. And each tuple in that set is arity 6. Because now we have the 4 data points. We have our label, our truth value, ground truth value. We have our predicted value to ship with that. And our test set should have a non-null value in the predicted label, index, which we'll call it P6, because that's what I put it in a second. Doesn't matter what it is, but we're calling it this one, the 6th index of the tuple. If we go to our data output, right, we need the same form. We need to take if we go to our training data output, we need the same form. We need the training data that we had analyzed to be ready to go. We need to combine it, join it with its label, which is difficult to see because it joins in, but the label line is right here. And then we're going to set, because we know that dealing with downstream to a set of tuples of arity 6 and arity 5 is mechanically complicated, to say the least, especially if you need to do relational type operations, which all your visualization packages need to do. Also, it is informative to know whether or not there is a predicted value, because now I have a way of queuing my visualization into what was training data. Essentially, if there's a null value in this index, I know, that that is a training that element was used in the training set, and I can flag it or mark it differently. And that's what I want to do, or that's what's in my mind for output. I want to be able to label the data that was used for training, label the data that was used for testing, and then demonstrate whether the predicted value matches the ground truth value. And including the null value and including the labels for each set allows me to make those logical comparisons later. But what I can't do is ship these two tuples into Vega Lite side by side, or in a mixed array, or in a nested array. So I have to concat them. Concat is generally a cheap operation. And what we're seeing, though, is, and this is an interesting find for me, actually, because I had not thought about this formally or deeply until I was putting this presentation together. What we're seeing is concat takes an arbitrary number of our sets, an arbitrary number of data structures that are compatible with each other. You can think of the non-generic form of compatible in this case would be having iterables, excuse me. It's been a long day already, I guess. So if we have a bunch of iterables and we know that concat will ingest an arbitrary number of iterables and give you one iterable on the output, we can see that there is a difficulty of isomorphism here, because there is no way to know via the output set how many input sets there are. And if you have an input set of no nesting, so you just put in a single set into concat, there's no need to use concat. If we have two, we put it into concat. If we don't know what our input, if we're blind to the input, we can't trace the output. And from a computational perspective, if we step back to what I said about generating facts and having to parse facts and the number of facts we need to generate versus the number of facts that we need to solve a problem, and generally it being bad to have those two at a severe mismatch, needing to calculate orders of magnitude more than are needed to accurately decide. Operations like concat get really messy. This is why the fast versions don't respect ordering. This is why we have some kind of, we have a couple major implementations in different languages, whether you are actually rearranging the bits on disk or creating an array of references to individual memory structures, and why and how you would do that, or like SQL databases, relational databases, which are often going to construct a list of references to other data structures, and then basically do their own execution cycle in database on and how to wire those together. There's a lot of strategies for that. You can very strongly decouple them, where you have a database on one end, something to send it instructions. The database prepares the data, sends it to probably an intermediary server, and then back out to the client via your whole auth chain. That is ending up needing to do your operations in 2 or 3 different places, and anywhere you have touchdown points, pretty expensive. That is the common approach right now. In database compute is not a robust option. If you think about SQL is a great language. There's a reason it's stuck around, but doing robust computation with it is just not pleasant. And in some ways not possible, because it is a simple language and it expresses simply. My company's language is attempting to address that by giving a much more robust language to implement in database, and everything computes in database, but you've very much stepped into the land of how accessible or how realistic is this need to the day-to-day user, somebody like myself on the off hours who wants to track their finances. Do I go through the trouble of going through into this specialization to, when I can probably get away with SQL because I don't have much throughput. So I'm not suggesting one approach is better than the other. They have some advantages. They're certainly theoretically interesting. Why I mention that and why I'm going to sign off close to those points is that we have a lot of ways of managing these input chains. We have a lot of ways of representing this architecture in our code. This is really a language agnostic thing. We have to do each of these operations. That's because that's what k-nearest neighbors dictates, and that's what makes the algorithm informative. But we have a lot of strategies for how to pass data around and how to arrange our functions to generate those results reliably. So if we need to implement this in Python, we can do that. I've been working in Julia in my company's language. I can just as easily take this kind of logic structure and port it over. I understand where I'm working with sets and where I'm reducing and expanding values. And if I understand the language I'm working in well enough, I can start to order my choices of operation or my choices of functions and in data structures via the need for compression, expansion, indexing, joins, etc., and input to output. Excuse me. And then I can at least be somewhat assured that by the time it gets to the output stage, the transfers have been clean enough, or at least accountable enough, to give me a reliable data set to pass on and represent. And this is essentially how concat helps us. The concat intakes a problem and gives us essentially an isomorphism back, where it takes all the splatter and mess on the left side, turns it into a coherent set of single of a consistent arity, and then we can ship that out to our visualization function, which now can do the internal transformations it needs to do to present structured data via its API. And those are things we will never touch unless we are building that end as well. But I know for Vega Lite, this is a friendly and performant structure. If I want to stream this instead of shipping in, 150, eventually we're going to get 150 tuples back, by the way. Remember, we basically we peaked out at 90,000 to do our decision problem, and our output is 150. And that's one of those severe mismatches of facts generated versus facts necessary that I was talking about. And KNN is going to force us into that box in ways no matter what. So we have to accept that from the outset. There are ways to be cleaner about it and more intelligent, but I wouldn't get ambitious here. That has at least been my experience. However, this pipeline is rewarding. It's clean. It should be operationally stable if I deploy it and code it responsibly. And it should give me some options in terms of scaling around the volume of data that I have. Maybe we start with low volume and we need to scale up. Okay, well, we've got our operations reasonably defined anyway. If we can start to switch on streaming at certain points or some caching strategies, we'll know where and when to put those in. And we'll eventually be able to maintain downstream the way we need to, because we can scale our operations around the points that are fundamentally important to the result in the product, so to speak. And in my line of work, that's important. We've been doing a lot of work with industry clients who are interested in code accountability and accountability of larger scale operations. So this kind of work, and here's our final connected operation, becomes somewhat necessary in talking with clients and being able to say that I can show you how these boxes and arrows relate to the code that we are writing and deploying to solve this problem. And I think in terms of the future of machine learning, and you applying machine learning strategies to decision tasks, these types, being able to talk about in a rigorous way about the operations that you are creating and applying is going to be requisite for credibility and requisite for selling machine learning implementations. Part of this is definitely that I came from medicine, where machine learning is a very hard sell, because it's a lot of black box methods, and I have to have a deep accountability of what those are necessary for, what they are doing to the information, before most of my audience, who were largely physicians and surgeons, were going to warm up to the idea of using it for anything that resembled a serious task. They wanted much deeper accountability, and they wanted much deeper process accountability of the transformations that were being undertaken. And you can't provide those with things like neural nets and more popular large-scale machine learning strategies, which is not to say that is, which is not a criticism. Personally, I think our accountability is going to become a rising item. And so one of the enhancements here is I have an accountable system. I also have one that's repeatable and clonable if I need to re-architect scale. This is an easier, this reduces a lot of technical debt downstream by being clear and rigorous in its definitions. And where did isomorphisms come in? Well, we kind of got lucky. They live in the real world. They are rare and they're hard to find. But architecting around this principle of needing to doing minimum work to do data transformations, that's a good use, a good framing technique for applying isomorphisms. Does give us some strategies back that and does give us some strategic approaches, that we can apply to various problems that come our way. You're going to do more work up front to design and to spec out a system, but it will give you a little bit, or will give you a gain, in terms of communication, accountability, onboarding members to the project, turnover, these technical debt-related items. That documentation and report documentation and obtuse coding and logic structures tend to create as systems scale up. So yes, there's my pitch in a very quick form. Accountable operations, easier to identify where failure and variance takes place, areas that generate excessive facts. You can think about that as an increase in entropy. You can think about that as an increase of true versus potentially true information. And the resource allocation and planning is important for systems that are going from deployment environments, or prototype environments at small scales to production environments at high scale. It is very, very difficult to plan how to scale up. Very often you have to approach it in awkward ways. I think a lot of you are familiar with that. And then the important part, especially if this is client-facing work or I'm selling this, the thing that the people paying me or engaging with the work are probably most interested in are the endpoints, whether that's a data visualization API, a dashboard, some sort of product is going to largely be a representation, a very summarized representation of our process. And creating a stable interface there can help us keep the project on track and also keep our relationships managed. So I had the reference, if you want to look up that Fisher's data set, UCI has made it available. I had a couple references to Wikipedia early on. There, you can click those for definitions. I didn't put them in here. And then here's the Euclid distance function at the end, as I promised. But I'm actually going to turn it over. Thank you very much, everybody. And I will turn it back over to Courtney.
Thank you very much, Jason, for that. I know that there are a couple of people who are interested, who are watching, that are, somebody was like, I'm totally learning about accountability in school. So.
Oh, very cool. I'm glad. Hopefully it was useful to somebody, and I didn't not everyone just was like, oh, nod off to this guy. I saw him last year.
No. So if anybody watching wants to add some questions, we definitely have that time, but I do have a two-part question. So first, which parts of this are the specific elaborations or additions to the process which are necessary to achieve isomorphism?
Okay, that's a great question. And probably what we're going to have to do in this particular case, and I will qualify this answer heavily with a couple footnotes. So we'll start with those. One, this is an implementation specific response. Even if we change it slightly, these optimizations may break on us. And I know a couple PhDs locally in the area who have, a couple folks who have done work on optimization problems for their PhD work, and they'll tell you it's probably the worst idea to have an ambition for. They're the first people to try to talk you out of it when you're really going after it. And that's part of my reason for the qualification here is we can definitely overspecify this system, and I will be consciously taking a step in that direction, and I'm not saying that's wrong, but understand that the answer is not going to scale very well. Secondly, there is kind of a, if we wanted to increase the degree of isomorphism across end to end, we would probably want to think about, potential reasons for that. And we would probably want to have a list of motivating factors to go chasing that, because we're going to have to do some digging to make sure that the parts are tuned up. And so with those two kind of things in mind, I will attack the question, and hopefully this is a satisfactory answer. Where I would go to take on this difficulty of, or to take on this challenge, we'll call it, so to speak, of increasing the isomorphism especially in the KNN algorithm, I would be looking to reduce the number of times I have to re-index the sets that are being generated. So the number of times I have to run a loop of iteration are the thing that I would target for reduction. So the distance function has to take in two tuples and produce a scalar. There's no getting around that. So we're going to have to basically get to the next one. But if I can find a way to, instead of re-index, if I can find a way to reuse this index value in top, so instead of passing downstream where I'm going to need to generate some sort of ranking scheme on these arrays for this operation no matter what. I personally would like to do it once here, and then essentially we have the index getting passed with us along into the join. And then from the join, we can use, excuse me, I totally biffed that. Let me back up here. I would like to see this. I forgot that we have to do a count, and my this unique set problem crept up on me as I warned. So please erase that last couple of seconds, and I'm going to step back a little bit. We have to do the this. I told you this was a good question because it tripped me up, and I like that. We have to do this reduction here at the dist, and we have to do a sort here at the top. We're going to have to rank to get the K value. There are probably ways where we can just rely on a sort, or more heavily lean on a sort operation or a sort type operation than needing to generate this index along with our sort. So we might be able to define an operation that doesn't need these extra values, or has some way of being more efficient than having to rank everything. That would allow us possibly enough isomorphism here, but it would actually, the advantage of that is it would drop an entire column, it would reduce the arity of our tuples by 1, and that helps if we have a really long list. We're going to have to increase it here at the join because we need those labels back, and so we're stuck. What we can do, however, is to decrease the size of our set again. We can drop the distance metrics after we've joined in the labels. So we don't have to, we can pass in a smaller tuple into count. And we've basically preserved an isomorphism of sorts, but it's more, there's a big asterisk there where we've had to do an internal gyration. But that would at least prevent us from needing to transfer those data, and specifically to do the operations to make sure those the tuple of 3 is ordered. The operations to make sure those are ordered and well-matched tuples are what's expensive. So if we can drop a column, we do less of those operations because we're never getting away from them. Just how many do we do? And if we can recycle some of the information, operation, we can eliminate at that low level. The top function, what would be great is we have just a simpler way of scraping the top, but this particular function obligates us to rank again. If we didn't have to do that, we could definitely extract our label. However, I will have to warn you, unless we are taking the count, right? If we wanted to be really, and this is the caveat to my warning, or this is kind of the reason for my warning on where this can go sideways on you. If we're like dying to maintain an isomorphism here, we could take the count value with us. We could find a way to clean up this top and not have to index the set to get the first value that we want. And we could carry our count with the label. And then we would make this transformation isomorphic on the way out the door, or at least this step. I don't know that there's any value to doing that, but theoretically we could introduce an isomorphism there. So hopefully that addresses the question. I think those are the things we could do in the immediate to increase the meaningful relationships between the data that are getting passed. And under the hood, as these operations have to be tracked and done and redone, it would reduce kind of by orders of magnitude the number of times that we have to rejiggle sets, so to speak.
Okay, thank you. So another question was, what are some of the questions that you can answer with an isomorphism that without isomorphism would be answered in a I don't know, sort of fashion?
I think that's a great question, and if well, here we go. I will put a footnote on that as well. If I understand the question correctly, I think it's a really good thing to point out. So to the person who asked the question, please feel free to chime in if I misinterpret. What it sounds like to me is if we are okay, the first example that comes to mind, we are working on a Markov type process where we have we as people, right, we're standing here looking up and we can see certain events coming out at a pattern, but these events have hidden layers above them that are actually consequential to their rate, so to speak. And so if we're thinking kind of in terms of that, where we see one effect, but we want to dig deeper, we want more clarity in the process. How do we detect, or how can we be savvy to, perhaps is a better summary, to when these four states, or states 1, 3, and 4 resemble state 2 in output? And to summarize a very ADHD laden summary of that question, if we are blinded to the edges, so the arrows that go from node to node, how do we get a sense of what might be isomorphic versus not? That's how I'm going to interpret the question. So please feel free to direct the correction to Courtney if that's wrong. But I think that's a great question. And that is tricky. For one, that is where in talking to my coworkers internally, many of whom have PhDs in mathematics and probabilistic type operations, several of whom have PhDs in database design, and that is almost all set logic, by the way. So talking to them about this question this is where you have to get kind of somewhat tight, quote with your theory and with your ability to represent and specify your system, because it is a really hard thing to catch. And until you start digging into operations deeply, this slide I'm looking for, apologies, it is going to be a bit obtuse what is and isn't necessary. The mathematical algorithms, our VP of analytics would probably tell me well, this is why you go back to the math. The math algorithms tell you the minimum form of operation. It may not be realistic when you have data involved, because math doesn't care about data, but the data is somewhat arbitrary if the operation is valid, because they're provably, they work within well-defined boundaries. If you don't have an intuition for that, that's going to be, you're going to have to kind of backtrace it up the theory chain, so to speak. And so what I would say is these kinds of logical forms, and not necessarily describing your code, But if we take what's on the left here under naive KNN and we take it into like a functional programming approach, and we take our functions and we describe them more like this, and these would be, you know, f, you know, def, dist, parens, equals, right? I work in Julia. That's how you would do it there. So apologies for anyone else. But we would probably put a zip operation here. And if we want to describe this functionally, we still have these implicit, we still have these operations going on, and we still have these constraints. You know, these are still the operational constraints between them. We've just described them differently. And if we want to look at this in terms of like a functional, in a functional programming approach, we can take somewhat of an idea of like an interface boundary, or even probably a more direct example, specifying input and output types. So let's take our distance function, and I get to show off my Euclid distance function now. So you have to imagine this, by the way, as like a def f whatever thing. But the point being, if I spec this out to say it takes in R, which is an array, or a tuple of whatever length, right? And it takes an S, which is an array. I'm going to call them both tuples. The important thing about what the object that R and S are is that it's iterable, and they are of the same length. So length R equals length S, and they are iterable objects. And that is because we need to do this with it, right? That would be a zip operation, basically. And we are just going to take each of those. So we would do like a zip or like a sum or reduce operation on to take the subtract, to take the difference. And then this is a, you know, this is a reduce, or basically this is a map with x squared. So we're going to square each of these terms. Then we're going to sum that whole array, take the square root of it, and that's what gets returned. So our function signature is going to look, it's going to be tuple on the inside, and then down here we would have float, basically. That is a good way to get, that's a good cue that there's a reduction going on. And last year, somebody gave a talk on Boolean blindness that I happened to attend at LambdaConf. It was very good. Look it up. I cannot remember his name, but perhaps somebody else can enlighten us. And that's the condition we're looking at via that reduction. We've taken a bunch of information, and we've taken two tuples of arbitrary length, by the way. So it could be 2, it could be 2,000, it could be 400 million, and we've reduced them to a single scalar value. That is a good cue that we have some sort of reduction process going on, and we have information compression. And so we are probably looking more at a state like, we'll get there. We're probably looking more at a state something like the third one here, or even the fourth one. If our functions are very poorly defined, we'll drop information. But if we think of the x side as the variables parameters, and I apologize, I use the two interchangeably from statistics. But if we think of the parameters inside the parens for a function definition as the x set, and the parameters in the y set as our output of our function definition, our types and the data types that we're using to input output will give us at least a reasonably good cue as to how our parameters are mapping input to output. And that's probably the most direct or concrete way I can field that question. But it's a very good one, and I think it's worth thinking about. What I've shown you here is really, if you want to get formal about it or you need to get specific, this would be kind of you would have those functions defined, and you would define something like this based on an architecture that was in your mind or something that you've already written. So yeah, hopefully that long-winded answer is somewhat sensible.
I think that at least mostly answered that question. He can follow up later if not.
Excellent.
So our next question so far is, what sense of isomorphism are we talking about? The algebraic sense, and what relations on the data point sets are we preserving?
Ooh, that's a very good question. Yes, I am definitely speaking from an algebraic and relational point of view. You've undoubtedly caught one of the looser points in the fabric of my presentation here. I was definitely skimping on that in fear of partly in fear of myself nosediving in. Um, what I mentioned, and hopefully this gets to the specifics of the question quickly. I'm going to make a bit of an assumption since I can't see your face or interact. If I really botch this question, please feel free to hit me afterward as well if I miss the point, because I think it's a well-formed one, and since I can't clarify it with you, I would like to make sure that I don't assume that I've addressed it fully. But inside of those algebraic relations, and yes, like a relational algebra type form. When I mentioned that this kind of set parameters are important, or these links internally between tuples are important to establish, because I'll use my company's database here as a good example. Each of these are technically independent, and how we combine them is we define an algebraic operation that says take x, y, z, or take w, x, y, z, and then go to each relation and start matching them based on the I column. That's how you would describe it longhand. So the relations between sets and the relation between tuples that we're using in practice, so to speak, are these index values that follow the data around inside the database that my company is building. And I'm trying to answer this more specifically, lest I get just too diffuse with my terminology. But what I'm doing here is abstracting over a lot of that detail. So I'm not showing how those relations are kept and how you communicate keeping those relations. But the primary relationships we're trying to establish between the individual elements, if we consider each of these values a single data point, like one of these dots, essentially, if we consider each of them one of the dots, the relationship that we're interested in has to do with the link that we logically establish between whatever index value we choose in one relation, whatever index value we choose in another relation. And we'll define those operations composably. But the fundamental tie between the data points is going to be this ordered index that we've introduced in a shadow form. This is one of the things that's computationally very expensive about the database. So in math, basically you would move these i's to the right-hand side in a sub-value, and we would be doing set combinations based on, and so apologies, I just thought of this. So this would have been a great way to start. One way to think of it is we are doing combinations under the hood in these operations. In this type of operation, all of our combinations under the hood, working on the fly with some complex stuff, are working with tuples of n plus 1. And what I mean by that is the plus 1 is going to be this index column. We have in the language that my company is developing, we have a lot of ways of specifying individually what index to use. Other languages like Datalog obligate you to more specific patterns. So if I want to combine petal length and petal width, what I'm going to do is provide a rule that says take this data element and this data element and join them based on the I value. And I can do that arbitrarily, but what the thing that we are actually operating relationally on is technically the data, the index value of the data, and then we use that to make the relation, and then you parse the data to do the operation. But in the background, this index value is following us everywhere, but I did not represent it here. So hopefully that gets at the. Hopefully that does justice to a quality and fairly complex question. Please feel free to get me offline if you like more or to provide more clarity. There's my email in the corner.
Thank you. He said that makes sense so far, at least, but he
Excellent.
may hit you up later.
Yeah, please feel free to.
So our next question, it sounds like one principle of your product is accountability. So is it true that you decided your solution requires isomorphic steps to achieve this?
That's a great question. And absolutely, I decided that. There's many ways we could have done this. Yeah, the company's product does require that. That's certainly been my angle. It is certainly coming from my time in medicine as well. Accountability has been a major theme in my work personally for most of my life. There was no way to get traction with the research that I was doing without having some rigorously accountable steps to the calculations. And so this model is very much in line with how I think and how it works. But absolutely, this is a design choice. It's this minimum set problem again. Let me see. Yes. With entropy, there's very rarely a single minimum set. Probably a better way to describe, or a more accessible, immediately accessible way to describe this is, if you think of the utility of the sine, cosine, tangent functions, and I'm talking about the ones that draw a circle, or if you're in a time series, they go up and down. The utility of these definitions and of these mathematical structures is that they can be fully described in a single period. That is an extreme rarity, and the double hyperbole there is appropriate, not millennial in this case. And why they're so useful and why they're so rare is we know what every change in inflection means. So if you give me a slope, I have an idea, and if you give me a slope in a direction, I have an idea of where on that curve I am, and I can predict where I'm going. The real world doesn't work like that. So basically, like if you think of that analogy with the sine function, that is a minimum set that has a single definition, essentially. And so if you pick a variable out of that set, we know what it means and we know where it came from because there's a set of one. Most problems in the real world don't have that luxury. And so if you ask me, and this is certainly the liberty I was taking with this presentation, you can make design choices in this gap. And that is why I chose to focus on isomorphisms. This is a way, there we go. This really is a way of this principle of trying to realize stricter forms of relations. One of my good friends who's an experienced electrical engineer, he likes to talk about this in terms of interface boundaries and interface boundaries between functions, and more in terms of, as I described it, between inputs to functions and the values that it provides out, and the relationship between the data and the input. But I chose this particular principle because it has been on my mind a lot in the past 5-8 years of my work. It is something that that's kind of part of my daily work now with the company and a lot of the clients that we're engaged with. I also think it has definitely improved my coding and my ability to produce the type of software and the type of code and deployments that I want to, because it is putting my eye on tracking more consequential elements. That is not to say this is the way to do it. In this case, some category theory was much more convenient for communication than a whole bunch of math that looks worse than this because it doesn't say top count. It's just a bunch of Greek symbols. We can do it that way. You can do this on the back of a napkin with pictures. I picked this, and I picked kind of target isomorphisms. You certainly could choose other design principles to sensibly architect the system, and in some ways that's probably a better choice. We can see here with KNN that design choice is directly antagonistic to some of the things that we have to do to execute this algorithm. But when it comes to communicating that, if you have either somebody who's really stuck on this, or somehow you get saddled with having to implement this, that kind of clarity of task, for me at least, reduces a lot of the practical frustration of dealing with it, and allows me to better advocate for what I think is a more reasonable approach. But to go back to the original question, yes, absolutely, this was a design choice. You could start from other principles. I think we can all agree on a diffuse set of what first principles might be, but we'll all start taking reasonable steps in different directions shortly afterward. So yeah, great question and great pickup.
Okay, so our last question, unless somebody hits us with a last minute one, is there any benefit to sorting the quote unquote train points by their distance from the origin? Then the distance only needs to be computed over a range rather than the entire set of training data.
That's a great question, and I am going to, hopefully you do not feel brushed aside by how I'm going to field the question, because I'm going to seem like I'm overstepping it by saying yes, absolutely, that is correct, and then I'm going to launch into a much more direct discussion of why that particular question excites me. This is pointing out, when I said over here, this is a strategy for reducing the overhead, a potential strategy for reducing the overhead of these operations. And when it comes to large data sets, these kinds of transformations ahead of time, which would be done here, or actually even before we created those sets more than likely, and which if you're lucky, and a lot of times if you're deployed right, you can do those on the fly reasonably well. This is a great optimization, and this is, I'm going to say it like an old school machine learning trick. You transform your vectors ahead of time via some sensible, you apply some sensible and low cost transformation to your vectors ahead of time, and your data are in a sense pre-formatted for the operations downstream. I did not do that. The specific reason that I have not been thinking that way is the data that I have been working with, this data set of several billion that I mentioned, is hashed. And so there's no advantage to using numerical tricks because all the they're just hash keys. So I haven't been thinking that way, which does not mean that which does not at all mean that this is a bad strategy. This would be a great way of pre-computing. It's also an extremely durable way of pre-computing. So if we wanted to go in and take these sets of relations at first, we could add a couple of relations with these values pre-computed, and that would put us, honestly, we would be striking out certain parts of our function. And sorry, those strikeout lines are arbitrary. So yeah, I think that's a great question. That's a great suggestion. If we, if I were sitting around work and somebody said, okay, Jason, figure out how KNN applies to this problem, and we were drafting our next efforts list, personally, I would be advocating for a strategy like the one proposed in the question be included for serious evaluation in the next round of improvements, because absolutely, the statistician in me is always in favor of doing something to the data to make it easier to process, because I'm always going to vomit more data into the system. And that's how I ended up in data engineering. But yeah, I think that's a great question. It is also, if for those who are kind of unfamiliar with data scaling, those types of strategies, and there's a whole family of them, are good ways to manage your overhead of large data sets and in the process, both processing and compute processing and storage. So thank you very much. That's a great suggestion and a great question.
All right. Well, I think that about wraps us up for today. Jason, thank you so much for this. Such a great talk. And you know what? An incredibly lively question and answer session. That was very enjoyable.
You guys have me sweating over here. I did really enjoy the questions. It's always, it always puts a smile on my face when I get some serious questions back from a presentation, when people are engaged enough to try and ask things that either expand or challenge points that I made. And when I hear it done in detailed ways, it's very exciting to me. So yeah, thank you to everybody who took the time to show up. And thank you to John Courtney and company for taking the effort to put this on. I know there's a lot more great presentations down the pipe, so don't stop with me. please, give our other presenters some reason to show up as well. I think it was Harry Carey or someone in baseball said, thank you to to all of you who made this event necessary. We as presenters need that. I will be in the audience in the future, so I've give some credit to the kind of infrastructure that's going on that enables this for me. So I hope everybody enjoyed it, we can all keep enjoying it because we've got plenty more to go. And definitely this will not be the high point. So stay tuned.